start with the 10th question now. We start with the question number 10. Right. Question number 10. Right. Okay, see what it says. Do the following for the given species. Do the following for the given species. Draw the existing structure, then mark the dipole moment of the bonds, and state whether the species is polar or non-polar. Yeah, those are the things they have asked, right? So the few things are NO3 minus, SO32 minus, and then SO2. Few more stuff are there, NO2 plus, what is XCF2, then you have BCl2F. Right? This question number 10, right? Okay. So we are supposed to come up with whether the species is polar or non-polar. Right? Okay. So to comment whether the species is polar or non-polar, right? First we need to come up with the naturally existing structure, the existing structure of the nature, right? So when we are thinking of the existing structure of nature, basically we have to draw that with the exact shape, with its exact shape, right? So let's draw the structure first of all. Then after we can think of marking the dipole moments and coming up with the polarity of the molecule, right? Okay, first thing, let's try to draw the structure. So NO3 minus, you can draw the NO3 minus like this. This is a Lewis structure, or this is normally a Lewis structure of a NO3 minus molecule. But this is not the existing structure in nature. The existing NO3 minus is not like this. This is just a Lewis structure. But the closest diagram which represents the existing NO3 minus in nature is the resonance hybrid of this thing. Why we are saying so? Because one can draw another equally stabilized structure by drawing the double bond here, and these two guys are with minus signs. Or one can draw the double bond here and come up with these two oxygens as minus. So there are three structures of equal stability available for the NO3 minus as Lewis structures, resonance structures. So that we have to think of the resonance hybrid, which gives you the properties of existing NO3 minus in nature, right? So have to consider the resonance hybrid. So let's draw the hybrid. The hybrid of NO3 minus would look like this, right? The hybrid. So you have to consider the hybrid, right? So partial pi bonds are there, plus charge here. The charges on these things, 2 minus charges are distributing on 3 oxygen atoms. So minus 2 over 3, that is the partial charge. So existing NO3 2 minus is this, represented by the resonance hybrid. Right now? So you have some 5/3 kind of a bond order, 5 bond order here. Right. First you have to come up with the existing species, right? Existing structure to comment on the polarity. Then we have to mark dipole moments of each and every covalent bonds. So when it comes to these two, the bond here, this guy is more alternative than this. This guy is more alternative than this. So dipole moment could be marked like this. Electropositive atom gets the positive thing, and the electronegative atom gets the arrowhead. So here as well, electronegative atom gets the arrowhead, and electropositive atom gets the tail here. So 3 dipole moments could be marked like this. Right now? So actually, these 3 dipole moments are equal with magnitude, because between same two kind of atoms, right? Then are with 120 angle to each other. So those will cancel off. This is referred to as a perfect shape, where your central atom is without lone pairs. Where your central atom is without lone pairs, and all the connected atoms are same. Such situation is referred to as a perfect shape. So with perfect shapes, your net dipole moment is 0. Your net dipole moment is 0. So your net dipole moment is 0. That means it's a non-polar species. Right now? Right. Let's try to draw the right thing for the SO32 minus. This is nitrate. Number 2 is SO42 minus. Sorry for that. SO42 minus. Number 2 is referred to as SO42 minus. Sulfate ion. Nitrate ion is non-polar. Let's come to sulfate. First, you need to draw the existing structure in nature. So it comes sulfate. Right? One can draw this structure like this. This is one structure, one resonance structure, one stable resonance structure of sulfate. But naturally existing structure is not like this, because we can think of resonance hybrid now, because few of equally stabilized resonance structures are available for sulfate. So the two 5 bonds could be here and here, here and here, here and here as well. So few more options are available. So that we have to think of the resonance hybrid. So the hybrid will looks like this. For the sulfate, no? So 2 5 bonds are delocalizing on 4 places. 2 5 bonds are delocalizing on 4 places. So one place gets 2 5 over 4. 2 5 over 4. 2 5 bonds are delocalizing on 4 places, right? 2 5 over 4 is the 5 bond order. That means 5 over 2 is the 5 bond order. It's not the complete bond order, but the 5 bond order is 5 over 2. Right? So we have lone pairs as well, like this. So, and if you need charges, -2 charge delocalizing on 4 places. So one place gets -half. -2 in 4 places. -2 in 4 places. So one place gets half. So this is the resonance hybrid. This is the closest representation for the sulfate appearing in nature, right? For the sulfate appearing in nature, this is the closest representation, right? So after writing the thing with the existing nature thing with the correct shape, then we should come up with the dipole moments of each and every bond, right? The bonding electrons are attracted to the oxygen, as oxygen is more alternative, so we can mark that thing like this: dipole moments. Dipole moment is kind of a vector with some magnitude as well as a direction. So these are the directions. So when it comes to these 4 sulfur oxygen bonds, those are with same magnitudes because same kind of 4 atoms are appearing, right? 4 bonds are appearing, right? So again, 4 same kind of dipole moments appearing, right? So where the central atom is without a lone pair and with 4 connected similar kind of connected groups. So again, this can be referred to as a perfect shape when central atom is not with any lone pairs and all the connected groups are same. Those are referred to as perfect shapes. For perfect shapes, the net dipole moment is 0. So this is also non-polar. It is also non-polar, right? That is for the SO4 minus, right? Okay, let's copy the next one. Let's copy the right SO2. Quickly draw the SO2 as well. Number 3. This is SO2. Right? SO2 would look like this. If you have to draw the SO2 with the correct shape, it will look like this. Right? So then we should mark the dipole moments to comment on the polarity of the molecule, right? So dipole moment of this bond, SO bond. So basically the electrons will be attracted towards the oxygen, which is more alternative than the sulfur. So these electrons will also attract towards the oxygen, more alternative than the sulfur the oxygen is, right? So towards the greater alternative atom, the head comes and the arrow tail comes towards the least alternative atom, right? This is how the two dipole moments of the individual bonds are marked, right? So that what will happen when it comes to the net dipole moment? So these we can think of a resource here, horizontal and vertical resource. So basically the horizontal resource of these two things will cancel off. Horizontal resource of these two things will cancel off, but not the vertical resource. So vertical resource will remain downwards. So basically you will end up with this kind of a net dipole moment, as vertical resource won't cancel off. This kind of a dipole moment will be the resultant. So in SO2, right? In SO2, you have a negative pole here between the two oxygens and a positive pole here on top of the sulfur. On top of sulfur, you have the positive pole, and between the two oxygens, you have the negative pole in SO2. So it's a polar molecule. It's a polar molecule, right? As net dipole moment is not equal to 0, it's a polar molecule. SO2 is kind of a polar molecule. Next up, NO2 plus. Number 4 is about NO2 plus. See, first draw the structure, the existing structure. So NO2 plus would look like this. If you draw it correctly, it would come up as a linear molecule, NO2 plus. So now mark the dipole moments of each and every bond. So with the NO bond, dipole moment could be marked like this. Towards the more negative atom, the positive, the arrow head. Towards the more positive atom, the arrow tail, the positive sign, right? So these two dipole moments will cancel off. Two dipole moments with the same magnitude but opposite directions. Two dipole moments with the same magnitude but opposite directions. So this will cancel off, right, giving you a zero dipole moment. That is non-polar species, non-polar ion, right? No poles with that NO2 plus, right? Let's come up with the XCF2. XCF2. See the XCF2. XCF2. So you can draw the XCF2. It looks like this. Xenon should have 8 electrons around it to come up as a neutral atom. So 2, 8 are there, right? So this is how the XCF2 looks like. It's a linear molecule coming from the trigonal bipyramidal electron pair geometry. From the trigonal bipyramidal electron geometry, it's a linear molecule, right? So there also we are with two same magnitude dipole moments but opposite directions, like this case, right? So again those will cancel off, giving you a zero net dipole moment. It is also non-polar. Right, another non-polar molecule, right? So let's discuss about the ultimate one, BCl2F. BCl2F. I write it here, BCl2F. I write it here. I have some space here, right? Okay, we can write. So this is the VI, no? VI. BCl2F. BCl2F, right? Let's write that thing. So B, boron, 2 chlorines with 1,2 angle, 2 chlorines, and some F again with 1,2 angle, right? So let's mark dipole moments. So these electrons are going towards the chlorine because chlorine is more attractive than the boron. This is going towards the fluorine, right? Now fluorine is more attractive than the boron, so going towards the fluorine, but these going towards the chlorines, right? As the chlorines are more attractive than the boron. But here what we would observe is, you can think of the resolves of these chlorine things. So vertical resolves of the two chlorine BCl dipole moments will cancel off. The vertical resolves will cancel off. Vertical resolves will cancel off, but not the horizontal resolve. So horizontal resolve will end up like this. But the BF resolve will be, BF dipole moment will be stronger than that. So you have two dipole moments but not with the same strength. So this is more strong than this dipole moment. BCl thing is weaker than the BF. BCl dipole moment is weaker than the BF dipole moment because the greater difference between the B and F than the B and Cl, right? So the BF dipole moment is stronger than the BCl dipole moment. So resource coming from the BCl dipole moment is weaker than the resource coming from the BF. So BF is stronger. So ultimately there would be a net dipole moment towards the fluorine side, right? So there will be a net dipole moment towards the fluorine side, right? So we can draw it like this. Net dipole moment can be drawn. These are the individual dipole moments, right? So net dipole moment can be drawn like this. So a positive pole is actually between the two chlorines, and a negative pole is at the fluorine corner. So negative pole is at the fluorine corner and positive pole at the two chlorines, right? So you have a net dipole moment that is not equal to 0. That means you are a polar stuff. This is not considered as a perfect shape, Lamai. For it to become a perfect shape, right? All the connected groups should be the same, but here the connected groups are different, so that it is not a perfect shape, right? It is a polar stuff, right? Okay, now this is how we are supposed to complete the question number 10, right? Now, okay, that is all about the question number 10, right? Let's do the next one, so you can complete the stuff here. Right now, just take a screen capture, Lamai, then you can complete. Right? Okay. Let's move to question number 11. Right? Let's move to question number 11. Right. Let's come up with the question number 11 appearing at the page number 9 of your workbook. Right? Question number 11 at the page number 9 of the workbook. Right? Okay. See what it says. The dipole moment of a certain dipole molecule AB is measured to be 4.8 into 10 to the power minus 30 coulometers. Right? They have given you the dipole moment of AB is given as 4.8 10 to the power minus 30 coulometers. Okay. Then the bond length of AB is also given. Bond length is normally written in R. No? It is also given as 160 picometers. 160 picometers. First question they are asking is calculate the partial charge on each atom. Right? Calculate the partial charge. Partial charge. Delta. Calculate the partial charge delta. See, So we know from the equation of dipole moment, mu is equal to delta r. Mu is equal to delta r. So that the partial charge delta is equal to mu over r. Mu over r. Right? So the mu is given as 4.8 into 10 to the power minus 30 coulomb meters, and r is given as 160 picometers. 160 pico means 10 to the power minus 12 picometers. So definitely you should apply the numbers in SI units. Then only you get the final answer in SI units as well. Right? When applying the numbers to this kind of a equation, always follow the SI units. That is why I converted the picometers to the meters. Then you will come up with the answer in SI units, right? So simplifying this stuff will give you a value like this: 3 into 10 to the power minus 20 coulombs, right? So meters means will cancel off. So it will give you 3 into 10 to the minus 20 coulombs. That is a partial charge on A and B, right? So it's like this, no? If you have A and B, if you are to consider this one is with greater eternity, and if you are to consider this one is with a greater eternity, this one is a low eternity, that means the partial charges will appear like this, no? That value is this amount. This partial charge is this amount, right? So the second thing they are asking, calculate the percentage ionic character of the bond. So calculating percentage ionic character. So percentage ionic character means, what is that? The percentage ionic character means there's the equation for the percentage ionic character, no? The equation is percentage ionic character is given by the charge, the actual charge, the delta. Delta is the actual charge on atom divided by charge on atom. If 100% ionic, if the bond is 100% ionic, into 100. That is how the percentage ionic character is calculated, right? So we had found this. We had just found this, right? Now we are supposed to come up with this value. If we can find this value, then this can be divided by that value into 100 will give you the ionic character, right? Let's come up with that thing. Charge on atom if the bond is 100% ionic. Charge on atoms if bond is 100% ionic. That means if the bond is like this, see, then that is equal to 1 unit of simplest charge unit, 1 unit of charge. So it is equal to 1 E. The actual charge is not the -1 or +1, no? The Coulombic charge, what we need, no? The Coulombic charge, this is the relative charge, right? -1 and +1 is kind of relative charges, right? So actual charge, the Coulombic charge we need. So Coulombic charge is 1 unit of charge, 1 unit of charge, 1 unit of simplest charge unit, right? So 1 into simplest charge unit. So simplest charge unit is electron, E. So it says 1 into 1.6 into 10 to the power minus 19 coulombs. That is the charge on atoms if bond is 100% ionic, right? So from this we can say the percentage ionic character is equal to the actual charge, this value, the actual charge, the delta value divided by the charge on an atom if the bond is 100% ionic, this value. Into 100. This will give you a value like 18.75%. Right, no? So the AB bond is 18.75% ionic. Rest is with the covalent character. 81.25 of covalent character is there with the bond and 18.75 of ionic character with the bond, right? That is how you're supposed to do this kind of calculation, right? Now okay, so that is all about the question number 11, calculating the percentage ionic character. Right? Okay. So do the question number 12 at home. Right? Do the question number 12 at home. Right? Let's move to another question. Let's move to question number 14. So you can do the 13 as well at home, right? So do the question number 14. We'll discuss the question number 14. So I'll discuss 14, so you can do the 13 as well. So, right. So you can take a screen capture here. So then I'll continue with the question number 14. So these are stuff we have learned last day with the polarity of molecules, right? So let's do the question number 14 appearing at the page number 11. Right, this is question number 14. Right. Question number 14. See, let's try to do the 14, the page number 11. Right. See what it says. Draw the most acceptable Lewis dot dash structure for the PClNO2 minus ion. Its skeleton is given below. Right. So, number 1 is to draw the most acceptable Lewis structure of PClNO2 minus. Right, Lewis structure. See, skeleton is given there, no? O, N, P, C, L, and O. Right. So quickly, let's try to draw the most acceptable Lewis structure. So for a most acceptable Lewis structure, as you are with a minus charge, as you are with a net of -1 charge, better to put that -1 charge on an oxygen. Better to put that -1 charge on an oxygen. Right? Let's put the -1 charge on an oxygen for a most acceptable Lewis structure. So if the oxygen is with a minus charge, it should have only one bond. We have learned that, no? So if the oxygen is with 2 bonds while fulfilling the octet, it is 0 charged. If you are with lack of one bond compared to the neutral situation, you are with -1 charge. So oxygen is with -1 charge when the oxygen is with one single bond. So don't forget to complete the octet. Right. So after that, I am supposed to keep all of these atoms with the neutral form. If I can keep all of these atoms with the neutral form means 0 charged form, then that would be the most acceptable structure I can draw. So I am completed this atom. Then I'll go with this one. So for nitrogen to become neutral, it should have 3 bonds. It should have 3 bonds. 3 bonds with nitrogen, it is neutral. So to complete the octet, the 4th pair should be written. Okay, 4 pairs should be there around the second ornamental, right? That is done. So for phosphorus for the oxygen to have some negative charge, 0 charge, neutral atom, you need to have 2 bonds with the oxygen, completing the octet here, given the 4 pair situation. So that is done. So for a phosphorus to become neutral, right, actually if you have to think of the charge of the phosphorus here, 1, 2, 3, 4, 5 electrons are there, so no need to put any lone pairs there. So because with the third row above, you can have more than 80 electrons around you, right? You can exceed the octet with the third row above, right? So that it is okay to have 5 number of bonds around phosphorus, right? So in such a case, we should think of whether we need any electrons to keep this one at the 0 charge situation. So here with the phosphorus, as it's a group 15, it should have 5 electrons around it for it to become neutral. So here we have 1, 2, 3, 4, 5 electrons, so it is neutral, right? So for a chlorine, for a neutral chlorine, group 17 one, if your atom is group 17, right? For a neutral atom, it's better to have one bond there as a cone atom. So you need to come up with the remaining electrons, right now. So this is one most acceptable Lewis structure you can draw. Actually, we can think of 2 structures, right? This is one thing. So for a most acceptable structures, we can think of another one. even though they're asking for one, you can draw another thing, no? So if the skeleton was like this, you can come up with the other oxygen with the -1 charge as well, right? So one can give the -1 to this one as well, no? So with that thing also you can draw a better Lewis structure, right? So octet is completed, right? So supposed to have supposed to come up with a neutral charge. It should have 5 electrons around it. 1, 2, 3, 4, 5, as it is group 15. So these can be neutral stuff, right? Group 70 is with 1 bond, it is neutral, right? So for nitrogen to become neutral, it need 3 bonds. So if you are to put that third bond here, the oxygen is also neutral, right? So this is also acceptable. Both of these structures are highly acceptable, right? As most stable structures, right? Those are the answers for the question number 1, right? Roman number 2. The Roman number 2, they are asking for the oxygen numbers of nitrogen and phosphorus in the structures you have drawn. Oxygen states, oxygen numbers of nitrogen and phosphorus, right? So we'll draw for both. Oxygen states. So how do I relate? So with this nitrogen, what is the oxygen state first of all? Oxygen state means it is a charge on ion, charge on the considering atom, if all the bonds are considered to be ionic. If all the bonds are considered to be ionic, there is a charge on your considering atom. That is the oxygen state. So if you consider this nitrogen, right? So it is like this, no? So I'll derive the thing then better. No. So the structure would like this, no? Right? So if this bond is ionic, nitrogen gets a positive charge, oxygen gets a negative charge. Because more electronegative atom get a negative charge. If the bond is ionic, the electrons will attract towards that thing, no? Electron pair will be gained by that atom, no? So that is negative charge. More positive atom or the least electronegative atom gets a positive charge, right? So out of this bond, when it comes to these two bonds, nitrogen is more electronegative, so nitrogen gets some negative charge and phosphorus gets a positive charge. As two bonds are appearing, another negative for nitrogen and positive for phosphorus for the second bond. Out of these, phosphorus gets a positive charge, chlorine gets a negative charge for this bond because chlorine is more electronegative than phosphorus. Out of these two bonds, again phosphorus gets some positive charge while oxygen gets a negative charge for both the bonds because oxygen is more electronegative. So the charges around the atoms, right, when it comes to nitrogen, you have -1, -2 and +1. So altogether -1. Normally oxygen states are written inside brackets. It comes phosphorus, around it you have 1, 2, 3, 4, 5, +5. Right now, this is the working, right? So if you are thinking of this structure, I'll do the working for that thing as well. So as these two bonds are approaching towards the oxygen, electrons are approaching towards the oxygen because oxygen is more electronegative. Oxygen is a negative charge and nitrogen is a positive charge for the next bond as well. When it comes to this bond, nitrogen is more electronegative than the phosphorus, so nitrogen gets a negative charge, phosphorus gets a positive charge for this bond as well. phosphorus is a positive charge while the chlorine gets a negative charge because chlorine is more attenuated than phosphorus. For this bond, again phosphorus gets a positive charge and oxygen gets a negative charge, as oxygen is more attenuated than the phosphorus. So the charges around the nitrogen here is +1, +2 and -1. It's +1. Here it is +3. Right, that is how it looks like. So if you have drawn this structure, these are the two answers for the Roman number 2. If you had written this structure for the Roman number 1, these should be the answers for the Roman number 2. Right? Okay. Next one. Right. Let's copy the Roman number 3. Right. It's Roman number 3. Right. See, and actually Lewis structure for the H2CN3O2. What is that? H2CN3O2 minus sign. Okay, is given below. So the structure given there is this. The most acceptable Lewis structure is given. Right. Right, no? That is structure. Okay. And then what they are asking? Draw 3 more Lewis dot dash structures, resonance structures for this molecule and indicate their stabilities related to the structure given by writing stable or less stable or unstable. Okay. Right. The most stable is given. They are expecting us to come up with another 3 resonance structures. Let's draw. So we are supposed to complete the atoms one by one. Okay. Right. So let's start with this corner. Right. Let's start with this corner, giving this oxygen a negative charge. Right. Giving this oxygen negative charge. Let's start with this corner. Right. Okay. So I'll take it as a negative oxygen. So negative oxygen means only one bond is there. And oxygen is connected with one bond. It is negative. Right. Then carbon. Carbon carrying 4 bonds will be negative. Carbon carrying 4 bonds will be negative. So I need some ion with -1 charge. So I am trying to keep all the other atoms at a 0 position, at a neutral position, right? I have given the negative charge here. I am trying to put all the atoms at a 0 charge, right? That is my idea here, right? My goal here. So carbon with 4 bonds, it is 0. It is neutral. in the next atom. Unfortunately, we have to come up with a charge here, right? So nitrogen, it's a positive charge now with 4 bonds. We can't erase anything, right? So next atom, so nitrogen, and next atom, it's better to come up with oxygen here. So right, it's better to have minus there. Good, then to utilize charge. So the final thing, right? Final stuff, final two at once. Final two at once. So if we can keep both of these guys at a neutral situation, we are done. If we can keep both of these guys at a neutral position, neutral charge, we are done, because the summation of charges are now okay. So for a neutral nitrogen, you should have 3 bonds. You should have 3 bonds. So writing a single bond here will make this one as well as this one neutral. So don't forget to come up with the octets, the 4 pair situation. 1, 2, 3, the 4th pair. So this is kind of acceptable structure, right? Let's draw a few others. Right, another Lewis structure. So let's start with the positive charge here. Let's start with the positive charge here. Right, start with the positive charge here for unstable structure. Right, then it is better to come up with 2 negative atoms to come up with a total of -1. So carbon can't be negative here because 4 bonds are needed, right? So then the nitrogen. So if you come up with only 2 bonds, nitrogen will be negative. Come up with 2 bonds, nitrogen will be negative. So we need another one negative charge to complete this task, the -1. The next atom. Yeah, we can bring that minus charge with the oxygen. Right? Now we are supposed to keep the last 2 nitrogens at a neutral position. So a single bond will do so, complete in octets. So that is also done. It's a good structure, and it is referred to as an unstable structure because oxygen is bearing positive charge. We'll comment after writing all the 3 resonance structures, right? Third one. Third structure I'm going to draw now. So let's start with this cone as well. Let's start with this cone. Right, keeping this on a neutral is better, no? Right, okay. So yes, let's start with this. Right. So you have this thing. Let's bring up the negative charge. Right. Okay. So we can copy the positive charge here as well, no? Okay, better. So we need some different structure than this, no? We need some different structure than this, no? So I'm taking some positive charge here, right? So now my plan is to come up with some another negative atom, right? Another negative atom. So nitrogen can't get negative nature with 3 bonds, right? Definitely we have to write 3. I'm not going for 4 bonds because then it becomes positive. It's not good to get discharge, right? So now we are up to the final 2 atoms. You know, we are up to the final 2 atoms. So these 2 should have a net charge of -1. These 2 should have a net charge of -1. That would be possible if you are to bring some 2 bonds here. It brings some 2 bonds here. Carbon with 3 bonds carrying a minus. Oxygen with 2 bonds, 0 charge. Carbon with 3 bonds carrying a minus, right? So completing the octet, put the 4th pair on the carbon, and 2 pairs are already written for the oxygen, 3rd and 4th pairs. Right? So these are some accepted structures. So let's comment on their stabilities, right? So for this one, right? What about this? So here there's no reason to become unstable. There's no reason to become unstable. So you don't have similar sign charges on adjacent connected atoms, or you don't have a positive charge on oxygen, right? So there's no reason to become unstable. But you have some high charge dispersion compared to this, right? High charge distribution. Only one atom with charges here, but here you have 3 atoms with charges. So high charge, right, distribution. So it is less stable situation. Less stable situation. High charge distribution. High charge distribution is stable. Right now. This one. What about this? At the first place, we can see it is unstable because the most alternative atom carrying a positive charge. So this is unstable. Positive charge on most alternative atom oxygen. Next one. Here again there is no reason to become unstable, right? So when it comes to reasons of less stable, yes, there is one, because high charge distribution, right? So you have 3 atoms with charges here compared to only 1 atom at the most stable structure, right? So compared to most stable structure, you are with more atoms with charges. So it is a reason to become less stable. It is less stable. It is written as high charge distribution. Right? Okay. So that is how we are supposed to come up with. Right, no? Okay, this is Roman number 3. Let's quickly come up with the Roman number 4. Right. Roman number 4. Right. It says they have given you a structure. For the Roman number 4, they have given you a structure. And some questions are asked from that structure. No? For the Roman number 4, structure given is this. You have Br, P, O is there. Right, some nitrogen is there. The nitrogen with a positive charge. Some sulfur, fluorine and hydrogen. No? That is how it looks like, right? Some atoms are labeled. This one is number 1, this is carrying number 2, this is carrying number 3, this is 4, no? Yeah. So we have table to fill, right? Quickly draw this table, right? For those atoms, right? See. Yeah, 5 there, 5 of those. Right. Okay. One is the Vesper pairs. Vesper units. Second is the electron pair geometry. The shape. And hybridization. Then 5 is the oxygen state. Oxygen state, right? These are atoms P1, N2, N3, and S4. Let's quickly complete the table. Vesper pairs. Vesper pairs is the summation of sigma-1s and lone pairs. Summation of sigma-1s and lone pairs, right? So let's copy that. Right. Right. Okay. Vesper pairs. With the phosphorus. Summation of lone pairs and sigma-1s. 1, 2, 3, 4. It's 4. With the nitrogen, it is 1, 2, 3. When it comes to a double bond, only the first bond is sigma. All the other bonds are 5 bonds. So 1, 2, 3. With this nitrogen, only 2 sigmas are appearing. The other 2 are 5. 2 units. With this one, 1, 2, 3, 4. Sigma-1s and lone pairs, right? Only 1 sigma here. Other thing is 5, right? Here as well. The first bond between the atoms is sigma. All the other bonds are 5. First bond between 2 atoms is sigma. The others are 5. So we have 1, 2, 3 sigma-1s and 1 lone pair is 4. So if the Vesper count is 4, the electron pair geometry is tetrahedral. And the hybridization is sp3. If the Vesper count is 3, the electron pair geometry is trigonal planar. Hybridization is sp2. 3 units, 1 s and 2 b's. 3 units. If the Vesper count is 2, the electron pair geometry is linear. So 2 units means sp, s and a b, 1 and 1, 2. If the Vesper count is 4, it is tetrahedral. So the hybridization is 4 units means s and 3 p is sp3. Right now? Okay. So then we are supposed to come up with the shapes, right? The P1. 3 lone pairs, 3 bonded pairs and 1 lone pair. So coming up from the tetrahedral, if 1 is gone, you will end up with something like this, no? So tetrahedral structure is this, no? Tetrahedral structure is this. This tetrahedral, right? So 1 is gone. If 1 is gone, you are supposed to remove this one. This is tetrahedral structure, right? So if 1 is gone, this is removed. So this is the remaining, right? So this is pyramidal, no? Pyramidal shape, right? This trigonal pyramid. 3-phase pyramid. So if 3 units are there, the thing will look like this. Trigonal planar geometry, right? But if 1 is lone, you are supposed to remove one of these. So you will end up with what? This is bent or angular. N3 here, it is linear. With the linear electromagnetic geometry, only the linear shape available, right? There's no other shape, right? It's linear. So again, some tetrahedral geometry. So this is the situation. This is tetrahedral geometry, right? But again, one pair is removed. One is as a lone pair. So just this thing appears, right? This is trigonal plane, no? Trigonal plane. Trigonal plane, right? Okay. Sorry, trigonal pyramidal. Sorry for that, right? Trigonal pyramidal. Three-phase pyramids, right? Trigonal pyramidal, right? Okay. Oxygen states, we can apply the numbers, right? So from this bond, electrons are attracted towards the bromine, right? So it is negative, it's positive. With this, electrons are attracted towards the oxygen, it's negative, it's positive, the oxygen state, right? This is positive, yeah. When it comes to this bond, it is positive and negative. The electrons are attracted towards the more negative atom, so those gives a negative charge, the others gives a positive charge, right? The oxygen state is the charge on an atom when all the bonds are ionic, if all the bonds are ionic, right? So charge around the phosphorus is +3. What about the N2? See, when it comes to these two bonds, those are connected to same kind of atoms, right? No positive negative charge appears with these two bonds. So the charge on nitrogen is just -1 if all the bonds are ionic. That is the oxygen state, right? What about this? So no charge separation with this these two bonds, but with these, right? Nitrogen carries some negative charge while the sulfur carries positive because nitrogen is more important than sulfur. So this nitrogen carry -2. Because this sulfur, the sulfur fluorine bond, electrons are going towards the fluorine. So fluorine is minus, sulfur is positive because the fluorine is more important than sulfur. When it comes to this bond, sulfur is more important than the hydrogen. So sulfur gets a negative charge while hydrogen gets a positive charge. So the charges around the sulfur is +3 - 1, it is +2. So oxygen state of sulfur is +2. Right now? So that is about the table, right? So we are with few more stuff, right? Quickly complete the stuff appearing there, right? Okay. Then we are supposed to come up with the sigma bonds, no? The orbital overlaps. Orbital overlaps, right? Let's see. Orbital overlaps of the sigma bonds as well as phi bonds. First is about sigma bonds. So you have some bonds appearing there, no? Bromine and phosphorus, that bond. Then you have a sigma bond between the oxygen and P1. What else? Then P1 and N2. Then N2 and N3. N3 and S4. Few more. S4 and F. S4 and F. Then S4 and H. Quickly mark these things. So with sigma bonds, right, we are supposed to come up with the hybrid orbitals for the central atoms. We are supposed to come up with the hybrid orbitals for the central atoms. For the cone atoms, it is the ultimate electron field subshell. Ultimate electron field subshell, right? Atomic subshell, right? So for the bromine, it is not a central atom. Its ultimate subshell is 4p with the fourth period bromine is appearing. So it's a p block element. So 4p is its ultimate subshell. Phosphorus is kind of a central atom, so hybridization should be written. The hybridization is 1, 2, 3, 4 units, that is sp3. The oxygen and phosphorus. Oxygen, it's a terminal atom. The electron field ultimate subshell is 2p. The p1 is a central atom, so the hybridization is sp3 as earlier. The nitrogen is again a central atom, so its hybridization should be needed, as well as the phosphorus. It is also a central atom, so phosphorus is with sp3 hybridization. The N2, it is with 1, 2, 3 units, that is sp2. For the N2, it is sp2. For the N3, its hybridization is 1, 2, 2 sigma bonds and no lone pairs, 2 units, that is sp. The N3 is sp, and the S4 is with another central atom, so hybridization is needed. 1, 2, 3, 4 units, that means sp3. 3 sigma bonds and lone pair, 4 units, sp3. For the sulfur, it is sp3. Fluorine is kind of a cone atom, so the electron field final subshell is needed, that is 2p. So sp3, and for the hydrogen, it is going to be 1s. The electron field final subshell is 1s. Quickly come up with the 5 bonds as well. For the 5 bonds, we have N2, N3 5 bond, and we have another 5 bond between N3 and S4. See, so for the 5 bonds, always the p orbitals or the d orbitals can be used. You can't use the s orbitals or the hybrid orbitals for the 5 bonds, right? Okay, so N2 is this. So always with the second round orbitals, the 2p things are used for the 5 bond, because D's are not available with the second round orbitals. So always 2p's are used with the second round orbitals, because you don't have d orbitals now. So with the third row, it could be the 3p or the 3d. See, here it is 1, 2, 3, 4. The sp3 is the hybridization. sp3 hybridization means you are no longer with, right, p orbitals, 3p orbitals to involved with the 5 bond, because all the 3p orbitals are used in the hybridization sp3, right? So you have to come up with the 3d, right? That is about the 5 bond, right? Okay, then they have asked you the bond angles, right? The bond angles. So the bond angles, this is the 7th bond angles about P1, N2, N3 and S4, no? Yeah. N3 and S4. Right. See how to compute the bond angles. This guy is with a tetrahedral angle, tetrahedral electron pair geometry. Tetrahedral electron pair geometry means 109 and you have one lone pair. So 109 minus 2 is 107. Basically, first come up with the angle of the electron pair geometry, then deduce 2 units per lone pair. So tetrahedral geometry means 109, one lone pair is there, so 2 units are deducted, 107. This is coming with the trigonal planar geometry. Trigonal planar means 120. So one lone pair is there, so reduce 2 units. 120 minus 2 is 118. 118. For this one, it's a linear electron pair geometry, so no lone pairs, so 180. With the S4, the electron pair geometry is tetrahedral. Tetrahedral means 109, but one lone pair is there. So 107. For per lone pair, 2 is studied 107. Those are the bond angles. Finally, we are supposed to come up with the increasing order of the heterogeneity. Increasing order of the electronegativity of the P1, N2, N3 and S4. These guys, no? Increasing order, no? Right. See. So basically, first we have to think of the Pauling scale. According to the Pauling scale, nitrogen is always with a greater heterogeneity than the phosphorus and sulfur. So two nitrogens come here. First thing consideration is Pauling scale. Right? So the phosphorus is the smallest, sulfur is the next. So phosphorus is 2.1, no? Sulfur is 2.6, no? These guys are with 3.0 according to Pauling scale. So first consideration is Pauling scale. If the two atoms are equal with the Pauling scale, then we have to think of the hybridization and the stuff. So when compared to compare these two guys, N2 and N3, we have to consider hybridization. Here, the hybridization is 1, 2, 3. 3 units means sp2. Here it is sp. Greater the s character, greater will be the heterogeneities. So this guy is with great x character, 50% of his character. Then here is 33% just, right? So greater the s character, greater will be your heterogeneities. So N3 is with the greatest heterogeneity. So N2 is smaller than that. S character of the hybridization. Right, no? So that's it. So that's it for the question number 14. Right? So with this thing, we'll wind up for this session today.